Okay, we'll proceed with the next talk. So it's our pleasure now to welcome Jens Bardarson from Royal Institute of Technology in Sweden, who is going to talk about time evolution of local information, thermalization dynamics of local observables. Please, Jens.
Thanks, Ed. Well, let me start to thank you for the invitation to speak here. Of course, it would have been very nice to be in Korea and enjoy all the nice Korean food, but I guess that will be for other times. So this is a talk about thermalization dynamics, and it's work that I've done together with Thomas Klein Corning at UC Berkeley and Loic Herview. And Thomas is in the audience, and he will help with the discussion if needed. I should say that this is work that started when he was here in Stockholm, and then he basically went to UC Berkeley to finish the work, and I think it's fair to say that he has done, I mean, this is really his work. He should maybe be the first and last author of this work that just appeared on arXiv today. So that's the arXiv link. And since we were finishing the paper, I must admit that I couldn't spend as much time on the slides, so they're not completely polished as they should be, so I apologize for that. But I think the story is still there, and I think it's a nice story, and I thought it fitted well with this topic here, so I decided to tell you about this. So it's basically a story about understanding and simulating many-body quantum dynamics in systems that undergo thermalization. And just to have something concrete in mind, we can take this experiment here where you have some experimental way of preparing lowly entangled initial state. In this case, it's some kind of a charge density wave. And then once you have that initial state, you time evolve with some Hamiltonian. And you follow the evolution, and then maybe at the end you'll measure something. Right? If one likes, one can think about this as a quantum quench. You prepare psi 0 as the ground state of some Hamiltonian 8-0, and then at time 0 you switch to the full Hamiltonian, and therefore you do some kind of global quench. But that's not really essential. It's also just good to think about what the experiment does and think about some way of preparing an initial state that you then time evolve. But usually we want to think about the preparation generating some state which is kind of lowly entangled, and as time evolves, what really happens is that we get a lot of entanglement. And you know, when you follow these dynamics, then this is essentially the imbalance we saw in the last talk, although this is measuring only the density on the odd sides. And in the charge density wave, that the density starts at 0, and then it increases, and then it thermalizes to its thermal value, which here is half. And you know, you can do numerics with these, for example, using matrix protostates. And the solid line here is the numerics, and it follows the experiments up until some point. And at that point, the numerics breaks down. And you can kind of work hard to improve the numerics, and you can maybe go to a little bit larger times, but generally you cannot push the numerics very hard, much further. At least if you are interested in kind of simulating the exact dynamics. But you could say, well, I've captured kind of the essential stuff here, and what happens here in the thermalized region is not so interesting. It's just flat, essentially. But of course, that's not fully true. First of all, it's a little bit of an artifact of the observable that we're looking at, which is this local, which is in a sense has local thermalization, which is very quick, but doesn't have any tails. But we would like generally be able to, if only for kind of intellectual completeness, to be able to take the simulation also to the long thermalization time. Now, the reason these simulations generally break down has to do with entanglement, especially if I'm doing some kind of matrix protostate, which is the state-of-the-art algorithms. So let me define a few things. So if I take some subspace A in the full space, then I define the von Neumann entanglement entropy as the rho log rho of trace rho log rho, where rho A is the reduced density matrix obtained from the state of the system at time t. And generally in systems that thermalize, this entanglement entropy grows as some kind of power law. In diffuser systems, similarly, it would grow proportional to time. But that also means that if I have, let's say, a matrix protostate with some bond dimension chi, then that bond dimension that I need in order to capture this full state grows exponentially in time. And it's really this exponential that means that this breaks very fast, and any kind of improvements in my computer or whatever that I can make, I will maybe be able to push this a little bit. I mean, this is a little bit old experiment, so probably nowadays we can go a little bit longer. But if I want to follow the full exact dynamics, then this entanglement barrier is always there, and basically there's nothing I can do, nothing obvious that I can do to get through it. But at the same time, somehow the thermal states are simple. And in particular, if I thermalize at, let's say, infinite temperature, then I could use something like purification to write down a pure state that describes the thermal state at the infinite temperature, and that pure state would have very low entanglement. So it seems that, at least in terms of the amount of information that's in this amount of relevant information that's in the long-time state, that's not so much. So maybe one would hope that one could capture this. And one way to see that something like this is happening is just to note that it's not the state itself that thermalizes. If I look at the density matrix describing the state at any time, it remains pure at all times, and therefore it cannot be a thermal state. But it's observables that thermalize, and it's observables, local observables. So if I take expectation values in the state of some local expectation values, these are the things that reach thermal values. Sometimes you write this like this by saying, okay, well, this remains a pure state. It's the reduced density matrix that becomes somehow a thermal density matrix. Okay, and if you know, I can say thermalization hypothesis, the way that works is that somehow all eigenstates are equivalent. So this comes about by some kind of a quantum typicality. I mean, if I calculate this observable here and I expand in eigenstates, there is this fastly oscillating term, so I only get the diagonal terms. But this still seems to have some information about the initial state. But if the matrix element only depend on energy and not on the particular eigenstate I pick, which is what that eigenstate thermalization hypothesis says, then I can take this matrix element out and I just get the thermal state here. So the conclusion from this is really that the detailed entanglement structure at long times is not important. It's important that there is a lot of entanglement, because it's the entanglement entropy that kind of generates the thermal state. So I need to have a lot of entanglement, but the exact details of the entanglement are not important. And what is really happening is that there's a flow of information from somehow relevant to irrelevant degrees of freedom. And that flow of information is not specific to this problem. It's quite a generic feature of thermalizing systems. And there is a nice kind of analogy in classical mechanics. If I take a classical system and I want to describe it with some probability distribution, then I can kind of measure the amount of information in that probability distribution using the Shannon entropy. And then if I take the n particle probability density that follows the position and momentum of every particle, and I plug into this entropy here that probability density, and then I ask what happens during time evolution, well, then this entropy is constant in time. And that, of course, has to do with the fact that if I follow all information of this classical system, then I never lose any information. And this is kind of analogous to the fact that if I look at the full quantum state, then dynamics is unitary, and in unitary dynamics, the entropy, the entropy of the total state is always the same. So the generation of entropy in classical mechanics comes in once I throw away some information in this many-body states. Namely, I say, well, what if I am only interested in the one particle probability density, which is obtained by integrating out all but one particle from this n particle density? I can use this F now in the Shannon entropy, and this becomes actually essentially the thermal entropy. It has a second law, and Boltzmann's eighth theorem works, and so on and so forth. And once I know this F, of course, it's useful. The Boltzmann equation is useful because all or most observables of interest, for example, a current, let's say, I can obtain from knowing F by just integrating. And this is really analogous somehow to the reduced density matrix in the quantum case. But now once I want to write down a time evolution equation for F, namely the Boltzmann equation, I have this right-hand side which collects all collisions. And if I write down these collisions at some kind of rates, then I will of course find that these rates depend on two-particle probability density, because it's two particles that are taking place in collisions. So now that density I don't have in this equation, but I could write down a time evolution equation for this two-particle density that will depend on three-particle density and so on. And if I keep that hierarchy, I will end up solving the full problem. Of course, that's not what we want, and what is done in the classical case is that you have some assumption of molecular chaos, which says, well, just before interaction, let's assume that this two-particle density is basically just the product of the two single-particle density. And by doing this, what you're doing is that you're introducing irreversibility, and you're forgetting about information that flew to that went out to some kind of higher order correlation functions. So is there something similar we can do in the quantum case? So and in order to answer that, first of all, I need to understand a little bit more where and what scale information is in a state. So the first part of what I want to tell you is kind of introducing what we call the information lattice, which is a way of keeping a little bit more detailed track of the information in a state. And the motivation is essentially that I see that for local observables, I need to have a lot of entanglement, but not all entanglement is somehow the same. So I wanna find a way of decoupling relevant entanglement from irrelevant entanglement. Now, once I have kind of that way of describing the information, I'm gonna see how in generic dynamics that information flows around. And once we have these two things, we would like to try to use the insights from kind of this finer structure of the information flow to see if we can construct some algorithms for doing time evolution of local information. Okay, so what is local information? Well, essentially what I want to do now is that I want to be able to capture the time evolution of local observables exactly. But I only care about local observables, and therefore I'm gonna keep only track of reduced density matrices of certain size, up to certain size. So I have some, and let me focus on 1D in this talk. So I have some chain here, for example, and I define a neighborhood NLN as being the set of L sides centered at N. So This is N22, it's centered at 2 and has diameter 2. And then I define the L local information to be the set of all density matrices on such neighborhoods of a given size L. So then the question that I want to kind of understand is what happens to the time evolution of this L local information. And of course I can get this L local information, namely all the reduced density matrices, from the full state if I had access to the full state. But I want to think about it such that I never have to have the full state, because the full state is too complex for me to keep track of. So this is the only thing I want to keep track of. So I want to know how does this evolve, and this is kind of similar to in the Boltzmann equation where you write down a time evolution equation for f, and here you get some right hand side, which of course depends on the L+1 local information. If you think about when you take and it's L+1 for nearest neighbor and nearest neighbor Hamiltonians. But if I need to know L+1 to get the time evolution of this, then I have the same problem as in the classical case. So generally this set of equations doesn't close, because then I need a time evolution for this that will give me the higher order one. So the question really is there a way to replace the right hand side by some function which actually only depends on omega L? And this generally will be an approximation.
Sorry, Jens. There was one quick question from the audience. Jeff asked, "What is going to determine the size cutoff?" Maybe.
Yeah, I will come to that.
Okay.
It's an important question. Yeah. Now, of course, there are cases where this absolutely does not work, and that's when information that flows to large scales somewhere is important. And if that important information at some point comes back to the smaller scales, then of course if I've thrown it away at some point, then this doesn't work. An example is if I have non-abelian anyons, I have some information in long-range entanglement, I do some braiding, and then I bring back particles again, then the information comes back to the local scale, and then I cannot hope to capture that with something like this. I could of course supplement this with keeping track of the anion states and their braiding, but then that will of course scale exponentially. But in the absence of such things, I might still hope that this works. Okay, so I need a few quantum information concepts here. So I define the von Neumann information as the log of the dimension of the reduced density matrix minus the von Neumann entropy. And you can think this is essentially the number of bits of information I can get about the state rho. The maximum amount of information I get from the state rho. And if you think about a singlet, for example, if I take the reduced density matrix of a single spin, that will have entanglement log 2, and then I get log 2 minus log 2, which is 0, which is just the fact that if I look at the reduced density matrix of one spin, I cannot get any information about the singlet. And I will also need to know if I have two different density matrices acting on space A and B, and that A and B may overlap. Then I want to know what is the information which is in the union of A and B, which is not to be found in either A or B separately. And that's defined by this. It's the information of rho AB minus the information of rho A minus the information in rho B, plus then the information in the overlap of A and B, so that I don't double count from these two minuses. And it's called conditional mutual information, just because if I can also think about this as being three regions A and B, so that A minus the intersection and B minus the intersection plus the intersection, and then this would be actually the conditional mutual information. Now, if I know this thing, the conditional mutual information, I can write some bounds on how closely I can approximate a density matrix on AB that agrees on the, well, agrees on A and agrees on B, where these are the reduced density matrices, and that's given by this expression. And in some cases, certainly if this conditional mutual information is 0, then I can recover the density matrix on the bigger space from the density matrix of the smaller space. That basically means that there's no information on the larger scale that cannot be obtained from the lower scales. And here's an example of such a map. This is, I guess it's called the, I forget what it's called, twisted something, where you take the exponents of log of row A plus log of row B minus log of row A intersection B. And this particular map is nice because if the conditional mutual information is not 0, then there is a known bound on how closely you approximate the state here. So we will use kind of, so the idea here is that if I know, roughly speaking, if I know the density matrix on some subspaces, can I construct the density matrix on a larger space? And that would be similar to what I was trying to do before, that if I know the L local information, can I construct the L plus 1 local information from that information in order to get the time derivative? Okay, but I need to understand a little bit how information flows, and for that I want to introduce a decomposition of the total information in a state into local components. And I do it as follows. I just write this I row as a function, this ILN, where the INL is the information on scale L that you cannot find in any subregion of smaller scale that contains N, more or less. So in the 0 scale, so I0 is just the density matrix on every side. I1 is now then, I will put a point here. That's how I will construct the information lattice. I put a point here at L1, and that means that the information in this point is the conditional mutual information between these 2 points. So this is the information that's not contained separately in these 2 points. So it would be the information in the density matrix of these 2 points, and same here would be the information that's in these 2 points, but not separately contained in these 2 points, and so on. The information in a point at the top here is the information that's not contained in any subregion below it. So that means that this kind of information lattice has this triangular structure, and if I'm at the top of a triangle, the information in that point is just the sum of the information in all the points below it. And if the information at some scale, for example these red ones, is 0, what that means is that I can construct the information on that scale from density matrices of smaller scale. So basically I can construct the information here, which generally would require four-side density matrix. I can construct that just from 2-side density matrices. And then once I have done this, my information is local. I've introduced an additional dimension, which is the scale, and this is the space. So I have space and scale of information. And on this lattice, it turns out that the information also flows, and I can think of information as a local quantity. I can think of it kind of as a fluid or a liquid that moves around. And if I have nearest neighbor interactions, then by just saying, okay, the time derivative of this local information is used to define some current, then those currents only couple nearest neighbors as follows. And then I can also define a total current on a scale which is just the sum over all n on a given scale. So if I don't want to, if I only want to know how much is the information flowing from one scale to another, but I don't want to look at the detailed spatial structure, then I just sum over all n. And I will also define IL as the sum over all n, all IN. Okay, so now I take an example, which is a mixed field Ising model with longitudinal and transverse field, and I start with some initial states, which is just this, and I follow the information as a function of time. And what I see is that there is a decoupling here between local information, so this is the scale, and then there is this wave packet that flows to large scales. So for this particular setup, there's a decoupling between the local information that gets stationary at small scales and this flow of information to large scales. And if I look at this is now the information current, I see that the information current goes down at small scales. It goes all the way down to 0, and I have this wave packet again that's or peak in the current, which is flowing towards larger and larger scales. And once I have no current here in the small scales, I'm going to define that as something which has reached the local thermalization. And what that means is that the information in this part I can describe by some what we call an L-local Gibbs state, which is just a state which is e to the some operator which is a local operator. Okay, I see I'm running a little bit over time here. So let me speed up a little bit. Maybe I can take a few more minutes over my time if that's okay.
Yeah, it's okay.
Okay, so the dynamics doesn't depend only on the Hamiltonian, it also depends on the initial state, and here I take a different initial state but the same Hamiltonian, which is just identity matrix everywhere except that we take one spin at some central site. And in this case, you see that there is no kind of finite thermalization time, but actually at all times there is some current that is flowing between scales, and even at smaller scales you'll get this current here. And if I look at the current at long time, so this is at longer times, then it becomes essentially a constant slope here. So that means that it's not, I cannot just write, like here I could write down some local Gibbs state that will capture the state. I actually need, if I want to fully capture the dynamics, I do need to keep track of the fact that there is this flow of current, flow of information between small scales and long scales. And I cannot, here, coming back to the question that were asked, here there's a clear cutoff scale in my time evolution of the L local information. I can just pick some cutoff scale where the current has gone to 0. Well, here there is no clear scale, so the selection of scale here becomes unclear. But if I only care about local observables, then that sets the scale on which I need to keep the information. And so the kind of assumption that we now want to make is that in order to make the simulation to be exact, I need a way of kind of keeping track of this current flow here. So if I go back to the information lattice, then what happens in these things where I have these tails is that there is a constant current flowing at some value. But what I'm doing when I'm making a cutoff is that I'm putting a boundary in this lattice, and I have to do something at this boundary. And if I just put the state somehow to 0 at the boundary, I'm missing this current or this flow of information. So the question now basically becomes, what is the correct boundary condition to put on the state at this boundary that I'm putting on here in order to capture the dynamics? So let me just quickly in the last few minutes tell you how that works. So the exact dynamics, again, that would depend on L+1. The exact dynamics of the L local information depends on the L+1 local information, and this you can just see from the equations of motions. The time derivative of the reduced density matrix is just a trace of this commutator, and if I look at terms in this commutator, if I'm looking at this neighborhood here, then it will contain things like this, where there is a Hamiltonian operator that acts on one side of that density matrix, but it connects to the region outside of it, and therefore I need the L+1 information if I want to get this time derivative, because of terms like this. But now I want to approximate this exact derivative somehow using this, and I want to find this function psi, and I want it to be compatible with this dynamics, which means that it is defined such that there exists a L+1 local information, which is such that the psi of the L local information would be equal to this exact function on that psi tilde. So in a way, I want to find a way of constructing an L+1 density matrix from only the L density matrices. And this thing has constraints. It has, for example, the constraint that if I take the trace of this, of one side, so I go from L+1 to L, then I want to get the exact density matrix. So if I take a trace from scale L+1 to scale L, then I want to keep the exact data. So that constrains this function. That's one constraint of this function. And if that's the only constraint, if somehow there's a finite thermalization time, then I can just pick, for example, this L+1 to be the Gibbs state, or I can use the Petz recovery map. And then this psi, what it does is just it's a convolution of the phi and the mapping that takes me from the L local information to the corresponding Gibbs information. But this only works if there is this clear decoupling of the states. If I have the infinite thermalization time, so that I still have this flow of information current at all times, then I need to keep track. I need to have the. Essentially, I want a boundary condition where this is true, that the current at any scale becomes essentially constant if I go to large enough scales. So this will kind of influence the boundary condition that we want to put on, and it's basically the assumption here is that I only need to keep track of the current, but the information that's flowing from the small scales to long scales is not relevant for the local expectation value, but I have to keep track of this flow of information, because if I put a zero current boundary, then I may get reflection of information back into the local scales, which will break my exact evolution. So we basically, the simplest thing we can do is to pick some kind of a fixed law-like assumption, which is to say, well, the current at scale L into L+1, I'm going to say it's proportional to the information at scale L, and then this current is just the ratio of the information at scale L and L-1 times the current at scale L-1. These three things are all information I have in my L local information, and therefore I can construct the current. And from constructing this current, that constrains this sigma tilde. So basically from this current condition plus the trace, the condition that the trace of the sigma tilde gives me the L local information that I have, that determines this wave function psi. Now it turns out this is not enough to fully determine the wave function psi. There are more degrees of freedom left, and I'm not giving you the details of how to deal with these extra degrees of freedom, and what we choose there is just to minimize the total information. But But the essential point is this current condition plus this trace plus minimizing the total information that determines this wave function psi. And once we have that, we can do time evolution. And just to show you quickly that it works, this is again the same model mixed field dicing with this state here. And now I'm looking at here changing this scale L, and this is the diffusion constant. At small times, it's this diffusion. It's this. Well, just this expansion, and then we go to diffusion at long times. And this is the error that we make by comparing the diffusion constant at large scale with smaller scales, and once we go to this 9 here, we can get below 1% in accuracy. And just a quick thing that's the diffusion constant is maybe something in that particular case that you might think is perhaps easier. So we also look at spin expectation value on the central side, and this we capture kind of the thermalization tail quite quickly again and again with accuracy which here it's about 2% or less than 2%. Okay, I went a little bit over time, I'm sorry about that, but basically this is the summary and conclusions of this work. So the work basically consists of 2 parts. The first part is introducing this information lattice as a nice way of seeing how information flows in thermalizing dynamics. And by looking at the flow of information on this lattice, what we see is that, well, of course, information flows from small scales to large scales. That's what we would expect. But there is this tail of information current that goes all the way back, all the way to the small scales. And when we are making a cut in the scale of information that we want to keep track of, the key point is how to deal with this current flow. And we can construct basically a function that captures this current flow at the boundary. So we basically, in a sense, we're picking a boundary condition that keeps the current at the boundary constant. And it works pretty well. There's a lot of things now to check. Is the boundary condition we selected was a simple one. What is the best way to implement the boundary conditions? What happens if you have disorder or even dissipation? Principle, this can be extended to higher dimensions and so on and so forth. So thank you for your attention, and sorry for going over a little bit. Hope that's okay.
Okay, thank you, Jens. I think now it's good time for questions. Yeah, so Dominic was the first one to raise the hand.
Hi, thanks for a nice talk. So I have more of a comment, but I will be really interested in what you have to say on that comment. So in most of your talk, you basically equated spread of information with thermalization, which is physically that's not exactly the same, right? Because in classical systems, you have no entanglement. There doesn't need to be any spread of information, but still ice melts if you throw it into hot water. And the reason for the entropy to increase there is basically because the point of phase space wanders into the largest macrostate. Now, in your system, you defined a lattice and you basically equated energy states with bits or information. You basically equated information or the largest energy eigenstate with those states that are the most entangled, because the largest macrostate will just be consistent of those most entangled states. So you are basically using a proxy for thermalization by measuring information flow and entanglement. It's not, but the information itself is not the reason why it thermalizes. Or, you can define information flow is the reason, is the thermalization itself. That's a fine definition, but I don't think that's physical definition. So if you can comment on that.
Yeah, this may just be a matter of presentation, really. So I'm not saying that this. So in particular, what I really want is to somehow make sure that there is this information current at the boundary where I'm going to make a cutoff, that it doesn't ruin my dynamics at small scales. I'm not really assuming that there is a thermalization in making this assumption. In fact, I do think that these methods, as long as that they could still work in systems where you maybe don't thermalize. So it's true that this is not equivalent to thermalization, but I mean I'm motivating it a little bit there. So your points are valid. I mean I may have been, in the way I presented it, making a seemingly too definite, equality between the two. But you're right. I mean, it's not the same thing.
Okay, thanks.
Okay, so there was a question by Jeff.
Yeah, thanks. And thanks, Jens, for a very nice presentation. I have a technical question on your last slide. Well, two questions actually. Sorry, no, the conclusion slide. What determines the peaks of your currents is question one. And question two is, the envelope looks like it's asymptoting to some flat value for J over J max. Is that correct? What happens for larger T?
Let's see. So let's see if I understand your question. So you mean what determines this peak here?
Mm-hmm.
I mean that's basically just Lieb-Robinson velocity of information away from the small scales. So that's cool. And okay, and yeah. So maybe let's see. I probably had that second question was, I think. So this is the ratio of the current at this side, so not the smaller scale, but this side, and on the higher scales. And it's true that it somehow it becomes quite flat, so it becomes kind of independent of scale, and of course it's going down as well. I mean, that's true. Maybe I'm not misunderstanding the question, but
no, that's roughly what I was asking. I guess my question is then, how do you understand this?
Oh, I think it's just a kind of statistical arguments that in many body dynamics, the information or you flow from simple, or you flow from that from small scales to large scales, just because there are way more phase space, if you like, in this information space on large scale. So it's just statistical arguments would tell you that the information should flow to larger scales. I don't know. Maybe Thomas, do you have any? Insight on this?
Hi. So the reason why it becomes sort of roughly constant in this case is that the question, or
yes.
So this is a diffusive process, like the energy distribution sort of becomes more and more even, and like the information flow at let's say scale 6 here, just after a while there is like really no dynamics on its own, or on scale 6 the information just that passes through that scale originates from sort of the local information on sort of determining how much energy there is in the system, and as the system diffuses, energy leaves this information leaves the smallest scales, but the rate at that the information leaves becomes more and more constant as the energy distribution becomes more and more flat, and then of course the current then becomes more and more constant. That's sort of the intuition behind it.
Great, thanks.
Okay, thank you. Are there any other questions?
Can I ask a question?
Yes, of course.
Okay, so you showed this picture for this, I mean, the propagating peaks, and what do you expect when you do the same calculation for the integral system, which does not normalize? For example, in the transverse field easing model without longitudinal field.
I guess it would still be a peak that kind of goes to larger scales. Whether what happens to the tails exactly, it may be slightly different, but I mean that's something that we should, it's in the outlook as well, looking into that in more detail. I don't know. Maybe Thomas has looked at it. I don't know.
No, I have not done the calculation, but yeah, I would expect, as Jens say, that in general, like there will still be some information that leaves travels to larger scale, but there will be more information that stays at the smallest scales. Yeah, which will be sort of restricted to stay at the smallest scales. Yeah.
Okay, thank you.
I mean, probably one can get some information about. I don't know. I'm speculating now. It's being recorded, so maybe I shouldn't speculate too much.
So Dario, you had a question.
I wonder it. I mean, what is your, because I mean, you tested your approach to, let's say, a nearest neighbor Hamiltonian, which of course is fine. I was wondering, what is your expectation when you go to, let's say, highly entangled, I mean, Hamiltonians that are, for example, highly chaotic, highly entangled, with a high level of entanglement and so on. Do you think this approach works?
But let's see. So I mean, a nearest neighbor Hamiltonian can lead to high entanglement. So you maybe mean, what do you mean?
Suppose that you take some long range Hamiltonian, some.
Okay. Yeah. I mean, so in principle, at least, okay. If it's very long range, then maybe it will be complicated to define current. But as long as it has a finite range, even if it's not nearest neighbor, in principle, one can generalize these things.
Mm-hmm.
So I don't see any kind of fundamental reason why it shouldn't work. It becomes a little bit more complicated, but I just keeping track of the information. But I don't see any kind of.
Mm-hmm.
I think the conceptual idea still works in that case, and also in 2D it also kind of works. It again becomes just a little bit more cumbersome because you have to pick your neighborhoods in a certain way and so on. But then whether it works in practice is maybe a different question, where I think one just has to try it. I don't see a reason why it shouldn't work, but there certainly might be some reasons that it becomes very slow or something. I don't know.
And perhaps a silly question. I mean, if I understand correctly, your main result here is to, let's say, make possible to generalize the MPS approach when you compute time evolution and so on to cases where you reach high level of entanglement, because somehow you understand how to, let's say, how to put some boundary condition that allow you to go to large time. Am I right?
Yeah, so it's essentially, I think the way I think about it at least is that there's some amount of entanglement that's not so important to keep details of that entanglement. It's important that it's there, but it's not important to keep track of the exact details. But some of the entanglement is important, and if I do just a cut in the matrix protostate, then I will always pick the largest entangled Smith states, and these may not be the ones that I need for the dynamics. So this is somehow trying to find a way of picking the entanglement that I'm interested in and discarding the one that I don't need to keep track of.
Okay.
As you know, maybe one can actually make what I just said now explicit by trying to map this out onto matrix protostate. It's something we should probably do, but we haven't done. So that's kind of my picture of it. You know, that's at least it's trying to find a boundary condition on this cut that is a little bit more refined than just picking the highest entanglement Smith state.
Okay.
Okay, are there any other questions at this point? No? Okay, if not, let's thank Jens again for his talk, and now we have again 10 minutes break